abstraction. So here we have an abstraction around a string. I want to say to differentiate between ordinary strings, which can be anything, and HTML, which say excludes some JavaScript or something that might cause havoc. And so in a module where I define this, I'm going to not export the McH constructor. I don't want everyone in the world to be able to inject and project out of this HTML type. And so that gives me a safety increase. Yet, Haskell's new type mechanism gives us the ability to do this without any one-time overhead. In a running program, the bit pattern used by a string and the bit pattern used by an HTML will be identical. And so this is nice. It allows conversions to be free, like this one. Because it's always safe to convert from an HTML back out to a string. We might export a function like this. And this will have no runtime effect. It's a complete no-op. But if we look at something like this, now we run into trouble. Because this string list, even though this has operationally no content, we'll still have to go and allocate a new list as it walks down the list. And so that's sort of terrible. Right? We wanted a no-cost abstraction, and yet now this is linear cost. That's a big difference. And so one might think, gee, shouldn't the optimizer just take care of that? But GHC's optimizer works over its typed intermediate language, and so this effect changes the type, so it can't quite be a no-op in the optimizer, or in the intermediate language. So that's not quite the answer here. So now that I've set up the problem, we're going to look at the solution, and then also look at ways that this solution has affected the rest of the Haskell ecosystem a little bit. And so our answer to this problem is to define a new equivalence relation, and spelled with sort of an approximate equal sign. I'm going to call that coercible. And we're going to have a coerce function that says that when A and B are coercible, that in fact we can get from A to B. And we're going to want this function to take no time in a running program. So according to the example that I set up, we're going to want, as long as A and B are coercible, we want the list of A to be coercible to list of B. So we can lift this operation through lists and be able to get that string list operation to be free. We're going to use a type class. So we declare a new class, coercible, connecting A and B, and say that whenever A is coercible to B, list of A is coercible to list of B through an instance. And in fact, this is implemented. This has already been released in GHC 7.8, and it's spelled coercible in GHC 7.8, which is why I'll use that terminology here. So let's look at the implementation of it. We have this coerce function, which is going to go from A to B, and we want this to be free. So how is it going to be implemented? Well, it's just got to be magic, right? This does nothing. And what that means, though, is that all of our instances of coercible must absolutely be sound. If they're not, then that means that this free operation might, say, take an int to a bool if say, a user were allowed to write a coercible instance from int to bool. And so we want to prohibit that. So all of the instances of coercible are going to have to be generated by GHC. Users won't be able to write these themselves. So let's look at these instances. So we're going to start out with reflexivity, right? Any type A is coercible to itself. And from here, we might expect symmetry and transitivity, except those won't really work out because we want syntax-directed solving. But it turns out that when all the instances are accounted for, symmetry and transitivity are admissible. So this is a symmetric, transitive, and reflexive relation, but we don't have those instances directly. Now we look at what instances are created by a new type declaration. So here again, this is the same declaration from the first slide. And we're going to say that if a type A is coercible to string, then it's also coercible to HTML. Conversely, if string is coercible to type B, then HTML is coercible to type B. And the reason that we have to do it in this perhaps unintuitive way is to get transitivity. If we just said HTML is coercible to string, then we wouldn't be able to build transitivity from that. We can see an example of that here using these so-called unwrapping instances or wrapping instances. That if we have yet another layer of new type wrapped around HTML, which is subject to, say, extra validation, we want to be able to show that string is coercible to valid HTML. We start out with reflexivity. Then we wrap up in HTML using the top instance on the screen here. And then we imagine another instance that looks just like that for valid HTML, and we can wrap that and show that string is coercible to valid HTML. You might be wondering a little bit about abstraction. We started out saying that we wanted HTML to be distinct from string. I'm going to return to that a little bit later on. There is a good solution for that. We also are going to need instances created from data declarations. So here we have the maybe type, and we want to know that whenever A is coercible to B, that maybe A is coercible to maybe B. And so this is called a lifting instance. And these are also created for new type declarations because we might want to lift through new type declarations just like through data type declarations. Here's an example of this in action. So we also start with reflexivity here. String is coercible to string. Use a wrapping instance to get HTML as coercible to string. And then we use the lifting instance toward the top of the slide to show that maybe HTML is coercible to maybe string. Working with lists is the same way, and so this is how we get that coercibility that we wanted from the first slide. The problem is that these lifting instances are sometimes a bad idea. So here we have a type family F, and those of you not familiar with type families, a type family in Haskell is essentially just a type function. We can think of this saying that f of string evaluates to int, and f of HTML evaluates to a function on bools. And now we use another new type abstraction called to wrap up f applied to A. Using this, we can derive that unsavory coercibility relationship, saying that using a similar trick, similar derivation as the last slide, we can build up string is coercible to HTML using its lifting instance. And then we use its new type unwrapping instances to get f string is coercible to f HTML. But of course, we just evaluate that type to get int is coercible to a function on bools. And that spells disaster. So what's going on here? What's going on here is that we have two equalities bouncing around inside of GHC, and they just crashed into each other. So on the left here, we have nominal equality, which is the ordinary Haskell equality that most Haskell programmers are thinking about when thinking about their types. This is the one that we really think of as type equality in Haskell, and is written with single twiddle, and we can write that in Haskell code. On the right side, we have this coercibility relation, which is also called representational equality, and this, in contrast, is only true when the representation at runtime is the same. So we're going to have that representational equality be coarser than the nominal equality, because any two types that are considered the same in real Haskell code, we certainly hope that they're going to have the same representation at runtime. But maybe, like string and HTML, we have types that have the same representation, but not considered the same types in regular Haskell. The other thing to note about these two equality relations, to give a little bit more intuition, is that for nominal equality, conversion is automatic. GHC is going to apply these equalities as it needs to during type inference. On the other hand, representational equality requires a manual conversion through calling coerce, which is exactly what we want when we're introducing new abstractions like HTML. All of the type system features that we use in Haskell actually work over nominal equality, except for this one new one. And so here we have this type family F, and the type family F can discern the difference between string and HTML, and in fact doesn't respect the representational equality. And so it takes two representationally equal things and maps them to two things that are definitely not representationally equal. And this is sort of the source of the disaster. Okay, so now how are we going to fix this disaster? So we really need to differentiate between two different data type declarations. We need to differentiate between maybe, where it's safe to have a lifting instance, and where it's not safe to have a lifting instance. And so the way we do that is we assign so-called roles to the type parameters. So this is a role is attached to this type parameter A on either side. We'll see exactly the definition of this on the next slide, but I should say right away that this idea of roles is an adaptation of previous work, and this version is rather simpler than the last one. The last version integrated roles right into the kind system, so every kind now had a role associated with it. That makes this a little bit less expressive, but more flexible, and we'll see examples of that toward the end of the talk. So we have three roles available: nominal, representational, and phantom. And The idea behind these is that this sort of says how that type parameter is used in the definition of a data type. So an example of nominal is uh-oh. And what it means to have a type parameter with a nominal role is that type parameter is used in a way that its name matters. It matters whether we say uh-oh of string versus uh-oh of HTML. And accordingly, the lifting instance for a nominal parameter will look something like this. We see that the type variable n is the same on both sides of the instance. In this case, it's redundant with reflexivity, but if we had multiple parameters, there might be other parameters that are treated differently. Representational equality is sort of the one that, or representational role, is the one that I think we expect more often in Haskell. This is what most Haskell 98-ish types would have. So here, we see the lifting instance that we saw just a few slides ago, that maybe R1 is coercible to maybe R2, as long as R1 is coercible to R2. The last role is phantom, and that's for types like proxy, where the type parameter isn't mentioned at all in the definition. So that means that P1 and P2 might have no relationship at all to each other, but the two types will still have the same runtime representation. And as you might imagine, you could sort of mix all of these in a multi-parameter data type, and these rules will sort of just build up from that. So our type safety depends on getting the right role. So where do these roles come from? Well, they come from role inference. And our goal in role inference is to figure out what the most permissive role allowed for each type parameter is while still retaining safety. And we can think of this as sort of a constraint propagation problem, where in the data type definition we see where these type parameters are used. If one is used in what I'll call a nominal context, then that parameter has to get a nominal role. So for example, in the definition for uh-oh, we had uh-oh equals FA, and so A is used in a nominal context as passed to a type family. So I'm listing that as a nominal root here. And the naive thing actually works. If we just bubble up the constraint through all the data types, we get the right roles. With all of this in hand, we can actually prove type safety. And to do so, we use GHC's typed intermediate language that I referred to earlier. So at first, it sort of gets in the way of optimizing, and then that sometimes that caused this whole exploration. On the plus side, now we can actually prove type safety for a small calculus instead of all of Haskell, so it allows us to really look at this. Okay, so that's our solution to the problem. But how has it affected other people? The most direct way that it's affected other people is that we have an immediate application for this technique in an old feature. So here we want to take age, which is going to be an abstraction wrapping up int. But we have an instance for the num class for int, and we want to have an instance of the num class for age. Well, instead of rewriting the whole thing, we want to just take the existing one that we have and use those same methods. This feature's been around for a while, and before this idea of roles, you could actually use this feature to implement unsafe coerce. You could break the type system. Now that it's re-implemented in terms of coerce, we have safety. So that's good. Of course, though, when you're taking an old feature and adding more safety to it, you can imagine it's going to rule out some programs that were previously valid, and we'll see some of that in a little bit. I mentioned toward the beginning about abstraction, what was happening with that. If HTML is coercible to string, do we always want that to be the case? Well, not quite. We only want to allow those instances when the constructor is in scope. So a rule of thumb here is if you can do the wrapping or unwrapping by hand, then you can also do it magically through coerce. And so this means, of course, because instances we don't have control over import and export, there's a little bit of custom solving around coercible to get this to work. There's another abstraction issue that arises, and that is, so let's consider this map type. So we have a map from keys k to values v, and internally we're going to keep things in order using k's ORed instance. But we don't know the details of map. So the first thing to think about, should we be able to coerce from a map from ints to strings to a map from ints to HTML? Yeah, that's going to be okay, right? We take this data structure, and now we just want to consider it that the output type is different. That's fine. But now, if we want to think about, should we be able to coerce it in the key? Right? Notice the difference here is that now we're looking at changing the key type. That's going to cause a problem, because it's possible that the ORed instance for string is different from the ORed instance for HTML. if we allowed this coercion, then all of these functions over this map would now be making the wrong assumptions about the ordered instance and do the wrong thing. It's not actually type unsafe. We wouldn't have a type error, but we'd have an operation error. If we actually look at the definition of map, so here's a very naive implementation, just as an association list, we can see that K and V are used symmetrically in the definition. There's no way to infer that one should have a nominal role and the other should have a representational role. So the programmer must specify the roles via a role annotation like we see here. Of course, we don't want role annotations everywhere because then that would break all existing data type declarations. So then the question is, what should the default be? And this has created vigorous debate in the Haskell community. So one side of the debate says, we need to preserve abstraction. Maybe someone doesn't know about roles and doesn't put the right role annotation in and doesn't want their invariance violated. Right? If we had left out the role annotation on map, then map might misbehave if we coerce it wrongly. On the other hand, if we default to nominal, then most uses of generalized new type deriving would no longer work unless everyone went through their libraries and put in role annotations. So we decided to lean in the favor of backward compatibility, and we infer the most permissive roles. And so this allows generalized new type deriving to continue to work, but perhaps a naive library author who doesn't know about the role annotations might lose some abstraction somewhere. This is an ongoing conversation, and maybe in the future we'll figure out a way to migrate to the safer choice. So how has this affected other code out in the wild? Last year, roles were pushed to the development build of GHC in August. By the end of September, Brian O'Sullivan tried to compile all available open source packages on the Hackage server. Of those, a little over 3,000 compiled with 7.6.3, which was the most recent released version at the time. Only 4 of those 3,000 didn't compile because of role problems. And actually 3 of those 4 were real bugs in those programs. That maybe there was an unstated assumption about that all type families, say, had to respect representational equality. And so the bugs didn't necessarily trigger, but could have with a bad type instance. Only one package failed to compile due to the conservativity of roles. And so I think of that as a pretty good result, especially considering no one actually depends on that package. There's no reverse dependencies for that particular one. So that's the study looking in the past. What about the future? As it turns out, as we were preparing our final paper submission, an issue came up that might sort of change this story a little bit going forward. So the monad class is proposed to change and to get the join method added with the type seen here. But we might want to wrap up a monad in some sort of restricted interface. If we want to use generalized new type deriving in this scenario, we'll have the case at the bottom of the slide here. We'll know that restricted of MA is coercible to MA, but we'll want to get that wanted as part of the coercion of join. So, given that, can we get that wanted? Can we do it? Well, the first step is fairly straightforward. We can simplify on the outside. But then, we get stuck. Because M's parameters role might be nominal. It's not necessarily safe to simplify with restricted of MA down to MA. We don't know if that's safe yet. So we're stuck, and in fact can't do this. So for now, join is being kept out of monad so that GND keeps working. There is a proposed solution. We're still working out the details, and you can find it on that wiki page there. So I talked about added flexibility. Because roles are not part of kinds, it allows us to do this. So when we define the functor class, that's a higher kinded type class. And it means that we can apply functor to maybe and which have different roles. In the previous formulation, something like this would be impossible because the role was part of the kind. So wrapping up, we've provided a way of getting truly free zero-cost abstractions instead of just mostly free. It has a straightforward interface to the programmers based on type classes, something that people already know how to use pretty well. It's implemented and released. And actually, in the process, we explored that there's some sometimes subtle interactions between type abstraction and advanced type system features. And actually, OCaml has hit this also and has created the need for variance annotations there, also on parameters to data types. And it's not yet clear exactly what the relationship is between these variance annotations and roles. Thanks for your attention. I'll take your questions.
Plenty of time for questions.
Nice presentation. I enjoyed the concrete examples. Oh, am I supposed to identify myself? Phil Wadler, University of Edinburgh. So, this is an awful lot of work for something that maybe should be very simple. And it makes me go back to a choice early on made in Haskell, and made me wonder if it was a good choice or not. Miranda did abstract data types in a rather different way than Haskell did. So Haskell says, basically declare a new type and then hide the type constructor. Whereas Miranda says, here, declare that within this scope, you treat these two types, the abstraction and the representation, as the same, but outside it they are distinct. And using Miranda's technique, you can get as many free things as you want by defining, say, a function within the scope in which HTML is defined as being the same as string. By just saying something, it takes a list of string from a list of HTML as ID, and that will type check. But you need to do it within that barrier. You couldn't do it later. So there is a trade-off there. One reason we didn't do this in the original Haskell definition, by the way, is we didn't know how it interacted with type classes. Much later, Jeremy Yallop, who's here, in his PhD, he worked out that, oh, actually you can, the two methods, the Haskell method and the Miranda method, each can translate to the other. Mm-hmm. So in fact, it would have been okay for type classes. So perhaps we made the wrong decision, and we should have done it Miranda-like. I just wanted to get your take on the possible trade-offs there.
Yes, I agree. This is an awful lot of complication built on this feature, and whenever I've gotten in a conversation sort of with someone making that point, we end up that the problem is new type, essentially, which is what you're saying. So whether or not that works with type families is another question. So it might work with type classes. I would be worried about if you have a type that, if you want to truly consider these two types distinct outside of the module, it would make sense to be able to make a type family that could differentiate between them. And so you might end up with some of these same interactions. I'm not sure how that would really work out, right? I haven't thought about that in detail, but that's right now the place I think it might run into trouble.
Maybe we could get together with Jeremy and look at it offline.
Yeah, it'd be interesting.
Alexei Romanov, Huawei. I just want to know, you said that 4 types failed to compile, 4 packages failed to compile, but what I'd like to know is how many packages broke because of problems similar to ones with map. Right? So how many of these packages needed would need role annotations?
Yes. It's really hard to be able to answer that, just because, for the same reason we can't infer the roles for something like map. It would depend. I mean, this problem comes up whenever you have a data type that has an invariant based on a class. And so it's not clear how we would be able to sort of look out in the universe and figure it out. I mean, in base, I think we needed to add something like 2 role annotations. It wasn't that many.
Okay, thank you.
Ryan?
Ryan Newton, Indiana University. I'm wondering if I want the user to not be able to fabricate any proxy that they like, I want to give them a more restricted set of proxies. I was a bit worried that there were coercible instances in the phantom type role. What about in safe Haskell? Is the new safe version of coerce allowed in the safe subset?
So that was also a big part of the debate, and in the end the answer is no, it is not yet in the safe subset, and it's something I'd like to explore further, how we can get it in there because of issues like that. I think if we had the assumption that all Haskell programmers knew about role annotations, it could be in the safe subset, but that's not going to be a valid assumption for quite a while.
Is the idea that I manually turn things away from the phantom role if I don't want that capability to rest in the hands of users?
That's right.
Andreas Aber. So maybe the obvious question is, why not put these role annotations into the kind syntax so you can actually scale this to higher order?
Well, for some of the reasons that we put at the end, the reason that the original paper published in 2011 was never implemented was because it was just too big a change to the kind system. It meant that essentially every arrow in any kind would have to have a role annotation on it. And that was considered to be too much. And also it would prevent the flexibility of being able to define, say, a monad instance for data types that took a nominal argument, which actually comes up in practice. And so we would need to have maybe two different monads, one for nominal and one for representational. It has problems of its own.
Right, or some kind of polymorphism for these annotations. Yeah.
That would be the other way to do it, is to have role polymorphism, but then it's just more complication. And so, we felt that this was sort of the right point in the design space.
Great. Let's thank Richard again. Thank you.